Anyways, we can just start recording over here. So, anyways, hi. If you don't know me that well yet, my name is Daniel Johnson. I'm a fourth semester master's student here. My advisor is Dr. Sun. I work sort of at the intersection between machine learning and high-performance computing. And today we're going to be talking about my research, which I've given it the title, Protecting HPC Algorithms with ML. And then a more technical title of Probability-Aware Selective Protection for Sparse Iterative Solvers via Prediction of Software Impacts. And we'll get into what the hell that means. So giving this talk to AI Club, I want this to be sort of informative on the machine learning side, since I know a lot of you care about that. But hopefully you can also learn some stuff about HPC as well, since basically HPC is not done that much here unless you've worked with Dr. Sun. So a lot of times people go through KU all the way without getting exposure to this, and it's pretty cool. So anyways, let's get into it. So some background, what is high performance computing? The big idea is you solve very advanced problems with supercomputers or computing clusters. What are they? Basically, you can think of it as like a bunch of computers in a trench coat. Basically, they talk to each other to solve massively parallel problems much quicker. For this figure you see over here, that's basically like a dragonfly network, it's called. Basically, this is how you connect a bunch of computers together, basically, so they work together into one supercomputer. What sorts of problems do you do in HPC? A lot of times it comes down to scientific computing. So stuff like climate modeling, there's hydrodynamic simulations, sort of like in the bottom right there, you see this is a simulation of a ball falling into water. Looks pretty cool. And in the top right, this is something I did over the summer while learning some differential equations. And it's like a reaction diffusion experiment. Thought that looked pretty cool. There's also like cosmological simulations, so like how do galaxies orbit around each other, that sort of thing. And also deep learning tasks are sort of being introduced into it, like NAS, or Neural Architecture Search. Is super interesting. Basically, that's the idea is you have some large neural networks, and you want to know, basically for some data, what is the optimal architecture for that problem. And you know, with consumer machines, that's going to take a lot of time to figure out, to train hundreds or thousands of times. But basically, you can do that on a supercomputer and try to find out what are the optimal architectures, not just for like accuracy performance, but also like, does something have good enough accuracy while maintaining basically like a fast inference time or fast training time if you want to retrain. So anyways, that's the idea of the sorts of problems that you solve. But we're going to be sort of honing in on one part of this, which is pretty unique to HPC, which is the fault problem. So basically the idea is that transistors these days have very small like diameters, right? Like microscopic basically. So the idea is that single event upsets, basically the flipping of one bit, can be caused by like cosmic rays or nearby radioactive components in a computer or around the computer. They can threaten bit flips and cause some errors. So those can look like hard errors or soft errors. Hard error is basically like the bit flip causes something basically irreversibly damage the program or system. So basically, you can think of just your program randomly crashes, all the tests work well, what happened. So the idea of that is that sort of thing, you can't just like easily roll that back in the program unless you have specific built-in infrastructure for it. So there are some like hardware level things that you can do. I think there's something called error correction codes that can make it so it can detect when one bit is flipped. But then there are limitations, like I believe if 2 bits are flipped, then it might not be able to figure out the correct orientation. So in the end, basically checkpointing is used a lot in massive scale, like physics simulations on supercomputers. So basically, that's the idea of each X amount of time, you're just going to dump the entire state of the system to disk, which is a lot of memory, and it can take a lot of time. You can see at the bottom right, basically, as the size of the supercomputer goes up, obviously there's more state to be held, so the time required to checkpoint is going to go up quite a bit. So that is something that is kind of annoying, but you have to do, right? You don't want to just be running something for months and then have it crash and not have a checkpoint. So anyways, that's what hard errors are, but soft errors are the kind of more insidious errors, where basically your program doesn't crash, but basically something changes that leads to incorrect data. So this can look like maybe something in a condition flips, so you go down the wrong path. Or simply, say you're doing like an iterative process, maybe like a gradient descent, something flips. It's kind of hard to tell why did that happen. So the idea behind this of how it's usually solved is replication. That's the idea of whenever you're doing these computations, basically each one you do it twice. And if you do it twice, if they differ, you know that an error happened and you can fix that. You can do the operation again and be like, okay, this one's definitely correct. So that's what's used a lot of the time. But that's also kind of annoying, right? Because you can run them in parallel so the time doesn't change, which is nice. But that's like double the power, double the machines required, etc. And something funny in this area of soft errors is the Super Mario 64 upwarp incident. Has anyone heard of this? Yeah? Yeah? So it's the idea of basically someone was playing Super Mario 64, and then suddenly, without explanation, Mario like warped above a ceiling that he was under. And people have tried to recreate it a bunch of different ways, even like going frame by frame, creating the same inputs. And basically, while emulating it perfectly, the same thing doesn't happen. So the idea is something had to have gone on hardware-wise. So there could have been some sort of hardware malfunction that no one understands, but a lot of times it's attributed to one of these single event upsets, went in, flipped a bit in the Y position, and just it went up, which is pretty funny to think about. But anyways, like I said, these can happen by sort of physics reasons, like cosmic rays, alpha particles, whatnot, stuff I don't understand very well. Or hardware defect can also cause that, but I think that's less interesting than a cosmic ray forcing Mario to go upwards, right? So anyways, in the top right, you can sort of see over time what this has looked like. That's at Oak Ridge National Lab. These are some of their different supercomputers. And the y-axis is basically the mean time between failures. And so you can see the y-scale, a lot of them are between 5 and 45 hours. So that's pretty significant, right? Basically, these things do happen. And when you're dealing with supercomputers, with so many transistors under high power in such a limited space, basically these things do happen. So how do we fix these things better? We talked about how we can use replication, but we talked about how that's kind of annoying. So the idea behind this sort of work is we're going to take an HPC algorithm that we can sort of test on. We're going to inject soft errors into it because we don't want to just have our computers and wait for a cosmic ray to hit it. You know, that's not a very reliable experiment setup. So basically, we're going to take an HPC algorithm, we're going to inject our own errors into it, and then we're going to try to beat these basic schemes. So in this, what you're sort of going to want to look at is these red bars and these purple bars, where these red bars are no protection at all. So they're just doing it once. And basically, it will take, this is an iterative algorithm, it will take more time and if an error occurs. So basically, these purple bars are full protection. It's always 100% overhead, because you're doing it twice. These red bars, basically, sometimes the error doesn't really matter much. So it's pretty competitive just to not protect. But sometimes it's a bunch of overhead. It's a very bad idea to not protect. So the idea is we would like to beat both this red scheme and this purple scheme. And we'll get into these other two schemes a little bit later. But what are we working with? So the idea is we're going to be taking preconditioned conjugate gradient. This is a pretty standard HPC algorithm. in that we're basically just solving a system of linear equations, which is like a staple of scientific computation. So the idea is we're solving an AX equal B, where A is symmetric positive definite, pretty standard. But the idea is this matrix is very large and sparse. So basically, if it was stored in a non-sparse format, like all the rows, all the columns are all there, then it would take up more memory than you have, most likely. So it's stored in like an IJV value way. The idea is for each non-zero value, you're going to store its I position, its J position for the row in the column, and then the value. So basically, you only have as many entries as there are values, and these big sparse matrices will have a lot less values than rows or columns, right? So this is what the algorithm is that we're going to be using. It's used in like fluid dynamics, structural mechanics. Graph problems use this a lot because big graphs a lot of times will be very sparse. So this is what we're working with. So how do we set this up? Basically, we want to be able to inject errors into this, right? So we're going to implement our own version of PCG that can basically take an iteration to inject an error at. And then also the idea is it will take a position to inject the error at. Basically, in the loop, in an iterative solver, basically there's one dominating operation, which is this sparse matrix vector multiplication. So in one of the vectors in that computation, we're just going to choose a position in there to inject the error, randomly, that is. So the idea is I would encourage you to think of it sort of this way, with a grid with the iteration on the x, position on the y. So we're going to choose one iteration position pair to inject this. And the idea is when we inject this error, a slowdown may occur. So basically, you can think of slowdown as the number of iterations it takes with the error over the amount of iterations it would have taken if that error did not occur. So in this sort of diagram, you can see the red grid is basically what happened when the error did occur. And the black grid is like basically the amount of iterations it would have taken if that were to not have occurred. So basically what we want to do is we know the slowdown if an error occurs, and we know that we can protect certain elements. So what we want to do is relate the cost between those two, because we want to weigh, like, do we protect or do we not protect? So we want to weigh the cost between those two decisions. So the idea is we're going to say if we protect one element, that's one cost. That's our baseline. And then the idea is if we don't protect, there's going to be some expected cost, which basically here we can look at P is the probability that an error occurs in a run. N is just the number of possible positions, the amount of rows in the A matrix, that sort of idea. And then IO is just what we were looking at before, the black part of the grid. That's the error-free iterations. And IE is basically the error iterations. So when we're looking at what is the cost of not protecting, the idea is we take IE minus IO, which is like the amount of iterations that it caused, times the number of positions. So it's basically the area of that grid. That's the sort of cost that is incurred if it were to happen. But we have to normalize it by the probability of it happening, which the idea of that is P is just over the entire grid. But we're looking at one position in this grid, so we have to normalize it by basically the number of positions and the number of iterations. So that's the idea. This is the expected cost. If it were to occur, we normalize it by this probability, and it causes this slowdown. So now we know what is the cost if we do protect, what is the expected cost if we do not protect. And this is where we get into just a little bit of math, but it's not too bad, I promise. Basically, we want to protect when basically not protecting is a greater cost than protecting. So just simplifying this, look at this second to last line. This IE over IO is greater than 1 plus 1 over P. This is what it simplifies down to. And IE over IO is exactly what we said earlier. That's just the slowdown. So using this framework, we can make a decision to protect based on if the slowdown is greater than 1 + 1 over p. So if we were to know the slowdown, we know we can make a correct decision. And here's where, if you were thinking with your ML head, green flags start to go off. So basically, we want to know what this slowdown value is. And we have a couple of things to deal with, right? If we think about what do we have for each iteration and position, well, we know what iteration it is, and we know the corresponding row in A, and we know the corresponding element of B. So I'll spare you some of the data analytics, but the idea is there are some things that correlate with slowdown, and that's the iteration and the 2 norm of the corresponding row in A. Basically the size of the elements, it's like a distance metric. These 2 things end up correlating with the slowdown. So as you can see over there, the x is the error iteration, just like before, but this time the y-axis is the row 2 norm. So the idea is that these sort of blue dots, these are the ones where not very much slowdown occurred at all. But as you start to get more red, more slowdown occurred. So this is the idea that we did a bunch of experiments, and this is what we found, that this is the sort of correlation. It's sort of this, these mountaintops for this specific matrix. But we found that there is this correlation here, so this means we can probably predict on this, right? There's one little caveat, though, is that these correlations are matrix specific. So this is going to look different for a different matrix. So basically, we're going to have one model for each matrix, but there's a justification for that later. So now that we have these correlations, how are we doing them well? We're in a situation where we have low features and medium data. So that sort of tells me we should use just traditional machine learning methods. So the idea is that we're going to do a hyperparameter search, and we're going to optimize the regression, right? The regression R-squared. And so I'm going to be going just a little bit over these ML topics for those of you that do not know it yet. The idea of a hyperparameter search is sort of what you see on this right-hand side. We have models that we can tweak their parameters. Some of them make the performance better, some of them make the performance worse. So the idea is we want to search this space of hyperparameters. And there's a couple of ways to do that. Being a grid search, which is just you statically define a set of parameters to try, or parameter combinations. You can also do it randomly, which is a little bit less biased because in grid search, you are specifically saying what you want, whereas random, it just tries different things. But if you do it a lot, it will probably find some stuff that's pretty good. But then there's also some sort of smarter search methods. And that's the idea of you do a sort of pseudo-random search, but you're going to be biasing the search towards areas that you likely think are better. So that's the idea of a Bayesian hyperparameter search, and that's basically what I'm using here. Next, basically we're going to be optimizing R-squared, which is pretty standard. We're just going to be optimizing how good the regression does. And we're going to be using threefold cross-validation. So basically we're going to have a training set, a validation set, and a testing set. And so basically we're going to be going over this training set, validation set, and we're going to be splitting it in 3, and then doing all combinations of that, training on 2/3, testing on the other third. And for each model, we're going to choose what performs best over each testing set. If you want to learn more about this, you can take an ML class or Google it. Basically, I want to introduce these topics, so if you want to learn more, you can. So what models are we using? Like I said, we're going to stick to pretty standard ML. So polynomial regression, support vector machine regression, random forests, gradient boosted trees, and k-nearest neighbors. These are just very standard. Some of them you might think more of classification models, but they can sort of be tweaked to become regression models. And that's basically our setup. It's very standard, but it's shown to be very effective, as we'll get into. But I would like to ask, since we're in an AI club, and I know lots of people really like deep learning, why do you think I did not use deep learning here? I'll open it up. Going once? Go.
Is it because of the low features?
Yeah, that's a good answer. So yeah, the idea is, think about the strengths of deep learning, right? Basically, they're really good at picking out really advanced correlations between the features, which we don't have. We only have 2 features, and the correlations are like fairly standard, right? And deep learning is also really good about squeezing a lot of understanding out of lots and lots of data. Here, we don't really have millions of data points. We have like thousands. So in this situation, using deep learning would be sort of like nailing a hammer with a sledgehammer. Basically, it would be really like kind of hard to optimize. It would be hard to make it not overfit. It would be harder to hyperparameter search because it's deep learning. So the idea is that if you're using a sledgehammer, you might like bend the nail or miss the nail. It's kind of difficult. So we're sticking to regular machine learning methods, and that works just well, just perfect, as we'll get into. So let's see some results. These are some figures that I love. Left-hand side here, you can see for one matrix, this is sort of the ground truth between error iteration, row 2 norm, and slowdown. And then on the right-hand side, you can see basically a prediction on these results, on this data. So basically, you can think this is the testing ground truth, and those are our predictions. And it looks very visually pleasing. I might print these out. So as we can see, I'm not going to go into too many metrics on the regression, because as we'll get into, the regression metrics are not actually what we care about as much. What we actually want to be doing is making good decisions on whether to predict or not. Because remember, this is the thing we care about, was the slowdown is greater than 1 + 1 over p. That's our decision. So the idea is we take our predictions of the slowdown, and we use that cutoff. And we want to not necessarily find the best R² ever. We want to make the best classification metrics because we want to make the best decision, right? So we're sort of turning a regression problem into a classification problem. So as someone doing machine learning, one thing you might ask is, why not just make it a classification problem in the first place? Figure out not exactly where the slowdown is, but figure out if it's on the left-hand side or the right-hand side of this classification point. The answer for that is that would make your model dependent on p completely. The idea is we want to be able to vary p, and if you did that, you would need to have one model for each p, which is not very practical. Even in our tests, we have like 100 p's, as we'll get into. So we don't want to have hundreds of models, and if we change the probability, we have to use a different model that may be worse. So that's the idea. We're going to be using a sort of regression problem, translating it into a classification problem, and hopefully it will work out. You'll see. Good practice machine learning. What do the classification metrics look like? Accuracy, there's precision and recall. Precision is basically you want to sort of penalize false positives. You want to always be correct when you say yes. Recall is you don't want any false negatives to go through. You want to always catch. Those positives. F1 score is basically a combination of those two. And more important, which we'll get into, is an F beta score, which is sort of a shifting of whether you think precision is preferred or recall is preferred. And which one of these you use is going to be different based on your problem. But I'd say a good rule is to never really use accuracy, because sometimes that leads to very bad results on skewed data. If you have 900 yeses and 1 no, your model could just always say yes, and it's like 99% accuracy, right? But if we think about our problem, what should we use? Well, if a false positive happens, which means we protected something and an error did not occur, the cost is just 1, right? As we went through before. But if we have a false negative and we let an error go through unprotected, that cost could potentially be very, very large. Could be 100 times slowdown, etc. So that's the sort of reasoning of the decision why we should prefer recall. But we don't want to just use recall, because then you might have a model that just always says yes. So we're going to be using an F beta score where basically recall is preferred. So in particular, we used F beta where beta is equal to 2. So basically that's a combination of precision and recall, but recall is 2 times more important than precision. So those are our metrics. That's what we want to evaluate this on. What were some of the results? This looks like this. Basically, for this hyperparameter search, we got a best version of each model. So you can think this thing labeled ridge, that was the polynomial regression. Which polynomial regression model worked best in the regression? That's what this model is, and here are the classification results for that model. So each one of these bars in the group is a different metric, as you saw before. And as I said before, we want to prioritize F beta where beta is equal to 2. So you can look at all of these, look at the magenta, and whichever one is highest. Basically, we want to say that is our best model, that's what we're going with. So those are the sort of classification results. We can see that you're hovering around 0.9. We're making pretty good decisions. And these look different for each matrix, but some matrix, like polynomial regression and like SVMs did worse and others did better, but this is just one of the ones that looks satisfying. If you wanted to see others, I could show those as well. But anyways, that means that we've gone through all of the machine learning process now. We've gotten our model that we say, yes, this model is the best for projecting this algorithm. But we have this, we say it's the best. Basically, next we should do an evaluation of this. So we're making good decisions, but how does it actually work when it's employed? So the idea here is that we want to do more experiment runs, and we want to measure the overhead of our strategy. And for our case, overhead is this formula, where basically, if you hone in on this summation here, basically, you're going to think that this is IE times n, basically that entire grid. Add that to the number of protections you do. So that's basically how much time it took, how many operations it took, plus how many times you protected, right? And you want to compare that to basically the case IO times n, where no error occurred and no protections occurred. So basically, if you compare those two, that is going to be your overhead. And I say for all p, like I mentioned earlier, basically we're going to be discretizing this since we can't do this perfect continuously because that's an infinite number. So we chose 100 p's between 0 and 1. And what does this protection look like? That's what we see over there. Basically, instead of having the row 2 norm on the y-axis, basically now we have iteration by row index. So if we're thinking about an actual protection scheme of that matrix, this is sort of what it looks like. So basically how bright it is basically what the predicted slowdown of what we thought it was. So we can see when the iteration gets high or it gets low, it says, maybe we shouldn't protect those as much. But as you're near the middle, some of those might be more dangerous. And you can see it also varies by row. It thinks that this row is more dangerous than the row next to it. So that's sort of how you can interpret that. And like the other ones, some of these end up being pretty visually satisfying as well. So we figured out how to evaluate our model on the real life scenario of running this. How did that go? These are sort of the results for that. And this is going to be a lot of information, but I guess first, direct your eyes to this red bar. Basically, that's the no protection case like it showed before. When the probability of an error is extremely low, obviously no protection is going to be good, right? Because if there's no error occurring and you never protect, you're going to be doing pretty good. But the idea is when you increase P on this x-axis, when you start getting these errors, basically that's going to shoot up extremely quick. Your overhead is going to skyrocket because errors actually are occurring. And you can sort of see this on the other side as well, except we can see that on that matrix, the no protection is actually kind of competitive to the others. So that sort of tells us that with that matrix, just not protecting is pretty okay. It seems like most errors, when they happen, it didn't lead to a gigantic overhead. So what is the next scheme that we were talking about? That was full protection, which is just this black line at 100%. That's just always 100% overhead. Like I said earlier, we want to beat that. And then the other schemes that were showed before as well, I'll quickly go over those. Basically, this blue line is just a random percentage of elements protected. So just, we're going to vary from 1% to 100%. Which one of those worked the best? It turned out that protecting 98% of the rows at random turned out to be the best. It still does kind of bad for these matrices in specific. Then, for the pink line, that's basically a scheme that has been developed where you take just the row 2 norms, you're not incorporating error iteration. Basically, protect a flat percentage of the row 2 norms where the row 2 norms were the highest, right? So here, take the highest 98% of rows for row 2 norms, protect all of those elements. And even that, for this matrix, some of the matrices, it actually does very well. This one, it's just barely below 100. So that just leaves our smart protection, which this graph, again, very satisfying. The idea is when we have a very low probability of an error occurring, we're going to be matching the performance of no protection, which is awesome. Then, as the probability of an error increases, we are still beating every single other scheme, even when an error is guaranteed at probability equals 1. So this is pretty successful, right? We're beating no protection, and we're beating full protection, and we're beating previous schemes that other people have made. So that worked pretty well. Over on this other matrix, it's sort of different, right? Because we showed that if an error occurs on this one, it's really terrible. Whereas on the other one, if an error occurs, it's not that bad, right? Even on this one, no protection always beats full protection because full protection is always up at 100. But even in this case, when no protection is pretty good, we are still doing better. And these sorts of areas you're seeing around us, the error bars, those, since these are calculations of means, basically, over 1,000 runs, basically this is the 95% confidence interval of that mean. So we are very confident that our scheme is pretty good. So these are sort of the main results that we got. We think about it from the beginning. We have our problem that is, should we protect elements or not? We don't like full protection, we don't like no protection. So what do we do? We can make a good decision when we know the slowdown. So let's train a regression model to figure out these slowdowns, convert it to classification by this cutoff, and then what we're going to do is we evaluated it over actual runs of the algorithm and saw that it worked as well. So that's a big summary of basically what this work is. We'll be getting into future work and stuff, but are there any questions as we go into this? What's up?
how do soft errors just cause slowdowns rather than failures?
That's a good question. So basically in this, we're basically injecting an error into the sparse matrix vector multiplication. So in that example, basically the result of that operation is just going to be incorrect. So basically in this, basically in our methodology, we inject it into a place that is the most common, but it's not in the control flow of the program, so it doesn't lead to basically unexpected errors and that type of thing. But if you think of the probabilities of this, basically our data is going to be, the main part of our memory. Basically, a array could hit the instructions as well, but usually in these sorts of applications, and pretty much all applications now, the data is much, much bigger than the instructions, right? So basically, the majority of the case is that it's going to hit one of these matrices, one of these vectors, where it would just essentially make the answer more incorrect for an iteration, and then it would keep doing its gradient descent, sort of. So that sort of answer? Cool. What else do we have?
So then,
Yeah.
sorry, a quick clarification question.
Sure.
I'm pretty sure. So then you were using the ML models to help you predict what to protect.
Yes.
Okay.
I guess that is sort of using a transitive property, right?
Yeah.
We are predicting the slowdowns,
Yeah.
and using the slowdown, we can make that decision.
Right. Yeah.
Yeah.
And then, so you said the model's going to be different for every matrix. So
Yes.
Then, if I I guess before I run my simulation or whatever, I need to first load the data into the model parameter search thing to train the model to protect my data, right?
Yeah.
So how long does that normally take to train the model? Sorry, I don't have as much of an ML background as I would like. So.
No, it's completely valid. So the idea is that the data here is basically we just do no production simulations, right? So we run, an error happens, and then we see the slowdown. So this can be done by just running your simulation over and over. This is how the data collection works, and it depends on the matrix how fast that's going to be. And it actually varies wildly by how, I basically think of it as how dangerous the matrix is. You can think of the left-hand side here as sort of a pretty dangerous matrix, since errors make it skyrocket pretty quickly, and the right-hand side is not very dangerous.
Right.
So most of our data collection, we got like 3,000 runs, where it's like 2,000 for training and validation and 1,000 for testing. And so for some of the matrices, that would it took maybe 5 or 10 minutes was the minimum. Some of them, we couldn't even do 3,000 in time. So I did 300, and that took 12 hours.
Oh no.
So
it just very much depends.
Very much depends, yeah.
Okay, that makes sense. And then a follow-up question to that, would it be possible to almost run the protection algorithm as the training of the model is almost like a sidecar thing to my simulation, such that instead of having an initial training step, I could start my sim, collect the data, so then as the simulation progresses, the protection would get better, if that makes sense? You're almost collecting data as you do it to then train the model in real time and apply it?
Yeah, I see what you mean. The problem is that basically when the error occurs, right, the next iteration is going to be different than if the error did not occur.
I gotcha.
So, yes, I do not believe that would be possible, because you can't just inject an error and also get the correct number of iterations outputted.
Yeah, I see what you mean.
But
'cause you do have to inject the errors to train the model. You couldn't. You'd have to you would need there to be errors in the first place.
Yeah.
Yeah. Okay.
So, I guess one thing you could do, sometimes this would be helpful, sometimes it wouldn't, is that basically whenever you inject an error, you sort of fork it in two different ways, right? You do your simulation up until the error point, then basically you do two different outcomes in parallel. One of which is you inject the error, get the data. One of which is you just don't inject the error, get your answer.
Right.
So it wouldn't be a perfect way. It would still be, introducing overhead to your simulation, but I guess that would be possible.
Okay. Okay, that makes sense.
Yeah.
Cool, thanks.
Mm-hmm. Any other stuff? Questions about the ML process and all that? Cool. One more important thing you mentioned is I said I was going to justify using one matrix for each one. That is part of this, which is the last part, just some future work stuff. We require one model for each matrix. I think it would maybe be possible to do a unified model for all matrices using other figures about the matrix itself. So just some examples that I thought of are just density, which is basically like the opposite of sparsity. So how dense is my sparse matrix? What is the average element value? So like not counting all the zeros. When I have values, what are those values on average? That could correlate. Then also, this is getting a little bit like deep learning mind. But if you got like really fancy, each one of these matrices has a sort of sparsity pattern. And in specific, we said it was symmetric, positive, definite, right? So it's definitely going to be symmetric. And each of them usually has some sort of pattern into it. And I suspect you could probably get some sort of embedding out of that. I don't know if there's been any work of trying to do like embeddings of how a sparsity pattern looks. But that sort of thing might also help this sort of unified model. But like I said, these iteration and two-norm correlations vary between models, right? So you would basically need to find a correlation between that correlation and some other matrix features, which may be difficult. I'm really not too sure. It was basically out of the scope for my work, but I think it would be pretty interesting. Also, basically, like I said, some of these experiments take a long time. So the idea is we limit it to 100 times slowdown. So basically, if our operation takes 100 iterations, we're going to cut it off after 10,000. Because like I said, these can already take a very long time to run. So if we didn't do that, it would just take tons more time. And if we think about the implications of this, this means that p has a lower bound, right? Because basically, if p got even lower, like 1e to the negative 3, that 1e to the negative 4, that means that the cutoff for the slowdown would be above 100. So, in our case, we wouldn't be able to predict higher than that. Or, I guess, having a lower p allowed means that we would be able to predict above that. But, like I said, these take very long. And also, we were talking about like very, very small p here, in which case, a lot of the times, no prediction is really just going to dominate. So you may only be able to match the performance of no prediction, which if we don't really know if we do for that low of level of p. We know when we get close, we're doing pretty good, right? But when you get even lower than that, the idea is that you're going to be fighting for a percentage point of overhead improvements. So that's sort of a justification for why we do this, and I think it's pretty fair. But it is still worth mentioning. So, what's up?
It almost makes me think, like, have you thought about, like, almost over time having almost like a DSI type thing, which it's getting kind of into the weeds here, but like you keep a cache of like the different models or like model parameters that you use for like a given matrix. So then you could maybe even have another model or just some sort of more simple prediction scheme where you can look at the matrix. Mm-hmm. Not necessarily on like sparsity or average element value, but just kind of in general, like try to establish some sort of correlation or something. Have you thought about something more general like that?
Sure.
If that made sense at all.
I think so. It's kind of reminding me of transfer learning.
Okay.
Are you familiar? Okay, so basically you train a machine learning model, right? Typically like deep learning model. you train it in a general fashion, say it's just like a general language model. The idea is you want to fine tune it to make it work with something else. So you might take a general language model, say like BERT, whatever, but you want it to be really good at answering like finance questions or whatever. Then you train it on another set of data, which is about like finance.
Okay.
So that's the idea. You train it on a general thing, then you train it again to make it good on a specific thing. So I don't know, it may be useful to like, I don't know, train it on like many different matrices and then use transfer learning to make it good on one matrix. I don't know.
Or you could even like kind of break it up into larger classes of matrices or something.
Yeah.
And then you could do it off like a sparsity pattern or something. And then be like, okay, we have like sort of general sparsity patterns, so then we can get it pretty good.
Yeah, you could even, yeah, depending on, the sparsity pattern, you could do some sort of like clustering to where you could at least cut down on the number of models required, and based on the results of that sort of clustering, you might be able to say like, these ones have similar features in this way, so we're going to use that as a feature to try to get a unified model.
That makes sense. Cool. Thanks.
Any other questions? Cool. Well, I'll chill around, but I guess I should have already been on this slide now that I think about it. But yeah, thanks for listening to me. This sort of work, basically this is my master's thesis work. We're going to try to get it like published this semester before I graduate, and then go work. So, thank you. You can see infinity again.
Whoa.